Hello everybody. We did 8.2 and we are doing already, this is the third lecture on 8.2 and believe it or not there's going to be a fourth one. I've spent a lot of time on this. It's an important part and I don't want to rush it. It's not so hard. It's just different techniques of solving questions. At least what we're going to do today again is just following the procedures. The next lecture there will be a bit of applications that might be a little bit tougher because there are kind of word problems, but that's not what we're doing now. What is the difference with what we have done so far is, I put it in caps here, non-homogeneous. So I remind you what we have. If an homogeneous one would, for instance, be an is equal to 2 times an minus 1, that would be homogeneous of degree 1, right? Because we only need one. Go back 1, that's a degree. But suppose I do a plus, and so whenever you put something here that does not depend on the an, of course if I put something that depends on an minus 2, it does not depend on some of the ai's, that's what I mean. So this would make it non-homogeneous. If I would put here 3an minus 2, that would be still homogeneous because it still depends on the ai. Okay, so I hope you see the difference between having an AI involved or not. Now, it doesn't have to be a constant. It could also be something like 4n, or we will even see something like another possibility is 5 to the power n, things like that. And I'll tell you what are all the possibilities that we will look at. So I'm saying these two are, if you have something in that it's non-homogeneous, if something in that you have homogeneous. Okay. Okay, but let's go to the one that I originally wrote down here. Let me get rid of everything else. Plus 4. And so how are we going to solve this? And there will be 2 steps. So step 1 is solve the homogeneous one. Anyways, you say, you're telling me, Professor, this is non-homogeneous. How can we do that? Well, ignore the part that makes it non-homogeneous. Okay, solve the homogeneous one, so that would be here an equals 2 times an minus 1. And step 2, find what we call, it's a weird, but it's a technical term, a particular solution. That means a solution of the origin of the non-homogeneous equation. Of the non-homogeneous form, okay? And then step 3, put them together. Now I have to explain each of these steps, but I just want to show you that there are 3 main steps and they all are kind of different things that we have to do in each of these steps. Now the first step we do know, solve the homogeneous equation. And I repeat, how do we get the homogeneous equation is by ignoring this extra term that is not depending on the ai's. And we solve that. So in this particular case, I'm gonna let's carry out each of the steps. I have to explain the other 2, but this one we at least we know. Okay, in step 1, we have to solve homogeneous equation. So for step 1, they have sub-steps like, so 1.1, we're gonna do the characteristic equation here. This is very easy. So an is 2 times an minus 1. This means r is 2, right? Because this is degree 1. Only have to go 1 back. Let me write degree 1. Sorry, degree is 1. And therefore we have to replace an by the r to the power of the degree and then lower the powers of r. But there is only 1 power of r, so that's why you have r equals 2. It's a very equal. It's actually solved already. So we know that r is 2 is the only root, and therefore the proposed equation, so we solved it already, okay, that was one to solve, but there's nothing to solve, it's already there. 1.3, degree 1s are extremely simple, that's why you never really get one, but I'm doing this for going quick over this thing. So now we have to propose the homogeneous equation, and the homogeneous equation is alpha So an is alpha 2 to the power n. Remember, what we do is, you take any of the roots, they become the base of the geometric sequence 2 to the n, and then in front here comes a polynomial of degree 1 less than the multiplicity of this root. Now this is a root of multiplicity 1, so this therefore is a polynomial of degree 0, a constant. But here we stop already. Solve the homogeneous equation, but so normally what we would have now is an initial condition. Okay, so let's add an initial condition here, and I think I want to take one that I had one here. What will I take here? Sorry, let me look in my paper. A0 is 1. But this is now the point where you have to be careful. I cannot find alpha just yet, because this is the initial condition for the non-homogeneous equation. This is the general form from the homogeneous equation, and that's not what I want. So I have to wait now. So here 1.4, instead of using the initial condition, what we normally do, I'm putting here wait. Okay, I'll see, we'll come back to this, what we have to do here later then. Now, step 2, this is where things are new. Find a particular solution. Okay, so this means we have to guess how a solution is going to look like, a potential solution look like, and then and we only need to find one. This says a particular means just one, and then we have to put them together. Now, how are we going to find potential solutions? I'm going to give you a recipe very soon, but for now I'm going to tell you, so propose, okay, I want to be a little bit careful now also with my notations. So we have to be careful because sometimes we're dealing with a non-homogeneous one, that's the one we're really interested in, but sometimes we work with the homogeneous one, what we did in step 1. So for the homogeneous one, I'm going to put a superscript h. Okay, let me write it a little bit bigger that you see what I mean to write here. So an superscript h is alpha 2 to the n. And remember, this alpha, we are not yet determining what this alpha is. We will eventually, but not yet. So I'm going to use this notation that I don't get confused with the actual an that I want to find, the actual solution. So now we're proposing a particular solution. Now it will not be the actual solution I want. For one simple reason, it will not satisfy the initial condition, most likely. By accident it could, but most likely it will not. So I'm also going to introduce a new notation, an with a little p between a superscript, and the p stands for particular. So the h stands for homogeneous, p stands for particular. So now I have to propose one, and okay, what is it and how I'm going to propose this? I'm going to tell you now, and later I will see why this works, that actually it will be just a constant. Now we have to be careful, we have already a constant alpha, and just to not get confused between the different types of constants, I'm going to use different types of letters here. I'm going to use capital letters. So the constant is a. So a is a constant, but again, I don't know yet what it is, as was alpha. But this one I'm going to start determining now. So this was, if you want, 2.1. You propose a potential particular solution, and in this case, it is a constant. We will see later that it's not always going to be a constant, but it's going to be more complicated, but we'll look at that. So 2.2, what do you do now? Now you plug in the original, so the non-homogeneous equation. So you plug this into this equation. So the equation was, I'll copy the equation again, an is 2 times an minus 1 plus 4, right? Okay, so I'm going to plug this in. Now that's not hard because it doesn't depend on n. What does it mean? I have to replace here, this becomes a, right? What is this? Well, this doesn't depend on n. In general, it will depend on n, and then it depends, then we have to change. This would be now the same value for n minus 1, but this is just a, and then plus 4. Now this is an equation in which we can solve A. So solve for A. Okay, that's easy, right? That is, if I bring the A to the other side, I get minus A equals 4, and so A is negative 4. So I find that my particular solution, A n p, is just negative 4. That is end of step 2. I have found a particular solution, meaning there is no constant anymore. But we still have this homogeneous one, and now, what is step 3? Said put them together. How? Very simple, we add them. So the strange thing is that if you take a particular solution, and we found one, here negative 4 is a particular solution because it satisfies the recurrence relation. It is a solution to the original non-homogeneous recurrence relation. And if you add to that any solution of the homogeneous one, you get a new solution. Now, we will verify that, but for now, we're just going to accept this. Put them together, so what we am saying is you take the homogeneous one, you take the particular one, and you just add them. And that is going to be the one that we want. The sum of these two. Okay, so let's do this. So step 3. So 3.1 is, let's put them together. An, the one that I'm looking for, is going to be the homogeneous one, but the homogeneous one still depends on alpha. And that's important that we have not yet found this alpha. So that is, so I'll write it here, the homogeneous one plus the particular one. The homogeneous one was alpha 2 to the power n, alpha times 2 to the power n, and the particular one was negative 4. So this is now the one that we propose. So what do we do now? Well, now we go back to this wait stuff here. So, okay, wait until step, what step is this? Step 3.1, step 3.2. But because in 3.2, what we're going to do is use the initial condition. Namely, A0 is 1. So that means if I plug this in here, I get a 1. If I put n equals 0, and on the right hand side, if I put n equals 0, I just get alpha and minus 4. So 1 is alpha minus 4, so we see that alpha is 5. And so the conclusion, therefore, is the solution is 5. So, sorry, let me write with an. An is 5 times 2 to the power n minus 4. Let's check. Let's check that this is actually correct. Okay, so we go back and I'm going to check that it satisfies my original equation, this is the original equation. I'll write it up one more time. So the recurrence relation was an is 2 times an minus 1 plus 4. Well, let's check that this, so check. But this is something you don't need to do, but if you have the time, why not, right? You have a whole day to solve a quiz. So what is the 2 minutes of your life to make sure that you didn't make a mistake here? Because it's easy to make mistakes with these things. So be very careful with that. Okay, so check. So let's check that. Well, we plug it in. We get 5 times 2 to the n minus 4 equals twice 5 times what? 2 to the minus 1, right? Because now the index is n minus 1. Okay. Plus minus 4. That is this guy, right? But then for n minus 1. And then plus 4. Okay, so I hope what you see what I did. I replaced an by the general solution, by the general formula. I replaced a minus 1 by the same formula, but now instead of n, I have n minus 1, and that I plugged into this here. That's what we get. So let's see, is this the same? So 5 times 2 to the n minus 4 is equal to, let's work this out, that is 2 times 5 times 2 to the n minus 1. It's 10 times 2 to the n minus 1, but actually if I multiply these together, it's actually better to do this way, because it's 5 times 2 to the n then, right? And then 2 times minus 4 is minus 8, so I'm working out the distributing there, plus 4. Is this true? Well, these two cancel, and then this checks out. Minus 4 is minus 8 plus 4. So this works. Okay, so the first thing that I want you to realize is this putting together, that you can find the general solution, you can find a solution then with the given initial conditions by using the sum of a homogeneous solution with a particular solution. Okay, so this is what we need to do. Now the one thing I need to kind of explain is where did this come from? That's the only thing that I have not explained. Okay, and I'm going to tell you this in really general right away. In the book they take their time to explain it, but I think it's even better to see it right away. And you'll see it's a little tricky, but not that much. Okay, so okay, I want to take here. Let me see. Okay, I'll do this one first. Sure. So how does it work? So how does our recurrence relation look like? It's a linear recursion relation. An is a certain coefficient, some number here. So I'm going to give some example, but I'm not going to work out the example because it's too difficult, but I just write down n minus 1 plus 7 n minus 3. Let's keep the n minus 2, why not? Plus 8 n minus 4. So this is degree 4 plus, and now comes an expression that let's call it f of n. Okay, so this is the part, this is the non-homogeneous part. And this is the homogeneous part. This is important because in step 1, we're going to use the homogeneous part. Okay? Now, f of n. F of n will look... This could be really any expression. You could have sine n there, e to the power n. You could have n factorial. It could be a constant. We have seen that. But we only will look at one type of functions that we can deal with. That's the limits of our methods is... And it is as follows. It is a geometric series, s to the power, a geometric sequence, s to the power n, so s is the base, times a polynomial. So here comes a polynomial of, and let's give it a degree d. Okay, so that's how it will look like. So there's a polynomial there of degree d. I don't want to write down how with general coefficients. That is not helping us much. So wait, let me see that I can get it, put it all together in one box. So it is a polynomial of degree d times Sn. And the degree is an important thing here. But there's another important information that I need. And m is the multiplicity of s as a root of the characteristic equation. Okay. So let's look at the example that we first studied, and let's look at did what I propose fit what I'm saying here. This was the recurrence relation. The homogeneous part, that's okay, and the non-homogeneous part was 4. Now, what is 4 here? How can I see 4 in this form? First of all, there seems to be no geometric part, no exponential part. That is because s was 1. So in the example here, so an is 2 times an minus 1 plus 4. f was a function of n, but actually it was not, it was just a constant. Okay, so what was s here? S was 1, correct? It's 1 to the power n. You don't see it because it's 1. That's the only one you don't see. Okay, what was the polynomial then? What was d then? The degree here? Well, yeah, so in other words, we have to now imagine. I'll do it in orange here. We don't normally have this, but let's imagine there is this 1 to the n. That is s is 1. Okay, so that's where the s is 1 comes from. What is the d here? Well, what's the polynomial then? Well, the polynomial is this guy, right? The thing that is in front of that power, and that is a polynomial of degree 0. So d is 0 here. Okay. Now, what about this guy, this m? What is m here? Well, what's the characteristic equation? Remember, the characteristic equation, we found that was actually a ridiculous equation. It was r minus 2 equals 0. R was 2, but let's write it as an equation, r minus 2 equals 0. So, what do I mean here with s? S is 1, right? What is the multiplicity of 1 in this equation? It's not even a root. Okay, then the multiplicity is 0. So I want to say this. M is 0 means no root. And the reason that I don't care about whether it is a root or not a root is because the formulas are the same. If I have to write M. Okay, so this is the data of the original thing. Now, so here is now what you propose. So given your Fn is of this form, with this information, you know, the three things that we know, let me color them. So there's the S here, right? That was, okay, let me write it in. There's an S. We had the D, let's make it red, so that the D was 0 here, right? And then we had the multiplicity, let's make it green, this M here, that was the multiplicity, so M was 0 in our case. And so what is the proposed particular solution? Remember, this was a particular solution, which we write with a little p, is going to be what? Well, first of all, it is going to be, again, a power of s, the same power of s, so s to the power n. That remains the same. Then, another thing that remains the same is what we're going to put here. In front of it, we're going to put a polynomial, but now not, this is a specific polynomial, right? Fn is a given function that we know everything about. In particular, in the example that we gave, it was the function constant 4. But now I'm going to put here a general polynomial of degree d. And I'll tell you a little bit what I mean with that, of degree d. So the same degree as before, as the one that the original question had. But it's a general polynomial, means its coefficients are a, B, C, D, E, that we later have to determine. That's the difference. Okay. And then, is that it? Well, unfortunately, there is the M guy. Where does the M guy come? Well, here comes N to the power that green M. So there are three components, if you want, three factors that we look at. Now, let's see what this means in the case of our example here. So in the case of our example, what should the particular solution be? Well, first of all, we have that S, which is 1. So we have 1 to the n, which we don't write, but I'll write it just then. Then this guy, this part, that's the general polynomial of degree d. D is 0, so a general polynomial of degree 0 means a constant. And that's why my A came from. And then what about the front part, n to the power m? Well, m was 0, so m to the power m, so this is n to the power 0. And therefore, the only thing we actually saw was a, and that's why we had a as our solution there. Okay, let's look at some examples here. So start with this one. an is 3 times an minus 1 plus 2m. Again, what is the degree here? Remember, how far do we have to go back? Again, 1. And that's going to make it very easy to do our calculation. So I'm keeping a little bit things a bit easy. And I'm going to take a1 to be 3. Notice that there's no reason that I should start from a0. An initial condition depends sometimes on what we know about this series, or the sequence, sorry, is that we sometimes give the initial condition at 0, sometimes we give it at 1. Perhaps the 3 doesn't make sense, or something like that, okay? Okay, so degree 1. So, step 1, the homogeneous. So the homogeneous equation is an is equal to 3 times an minus 1. So that is 1.1 if you want, 1.2, the characteristic equation. Now that's the characteristic equation is then r equals 3, right? If you want r minus 3 equals 0, but okay, so we solved it, r is 3, and then we propose a general homogeneous solution, and that is, as always, you take the root to the power n, and you multiply it with what? With a polynomial of degree 1 less than the multiplicity. What's the multiplicity here? The multiplicity is the multiplicity of this root. So the multiplicity of 3 is 1. Sorry, that's not the m that I was using above. Sorry about that. It's the multiplicity of this root is 1. So I have to put here a polynomial of degree 0, which means a constant. Alpha. Again, a constant. You're following that? Okay. Now remember, we stop here because we're going to put things together. So step 2 is now the particular solution. So 2.1 is we're going to propose a particular solution. Okay, so now we get to this determining these three quantities here. So how can I keep this inside of us? Okay, yeah. So remember what we look. We can analyze first our Fn. What is Fn? Let's write first down what Fn is perhaps. Fn is the part, the non-homogeneous part. In this case, that is 2n. Okay. So now there are three quantities that we have to determine. What is S, what is D, and what is M. Okay, so S first of all, so what is S here? Is again 1, right? Because actually there's no exponential part here. That means S is 1. Okay, what is D? D was the degree, let's see, D was the degree of the polynomial in front of that power. In this case, that is a polynomial of degree 1. So D is 1. Okay, and finally, what is M? D is 1. And what is M? M was the multiplicity, I'll write it up again, multiplicity of this guy, S equals of 1, in the characteristic equation. But the characteristic equation here, in the characteristic equation, in this characteristic equation, but it was not a root, therefore the multiplicity is 0. So, what does this now mean for our particular solution? We can now write down A and, okay, I'll do it here. A and P is equal to, well, S to the power 1, so I'm going to write it, 1 to the power n. Then I have to write a polynomial, a general polynomial, remember, a general polynomial of degree D. So a general polynomial of degree 1, that is A plus Bn, general, right? Okay, and then n to the power 0 here. So what I really have is A plus Bn. That's the proposed solution. What did we do then? Remember, go back to the step that we did here. The next thing is we're going to plug it into the original equation. Okay. And because what we need to find is A and B. So plug in. So 2.2, plug in. So where is our equation here? This is our equation. We see it. We have it here. Okay. So we have An, that is A plus Bn, equals 3 times the same guy, but replace n by n minus 1. So A plus B times n minus 1 plus 2n. Do we have to replace it n by n minus 1? No, that's what it says here. Just copy what it has, 2n. Okay, so that's what we have. Now what do we do? Okay, first of all we expand here, right? So we have 3a plus 3bn minus 3b plus 2n. You see that? Okay, I'm expanding this one and also multiply with 3 here. Let's take the terms with and without n. The constant, the degree 0 and degree 1 terms. The degree 0 terms are 3a minus 3b plus, and then we have 3b plus 2n. Yep, okay. Okay, so what does this now mean? Okay, so we have, this is an inequality that has to be happening for all values of n. In other words, this means that this polynomial must be the same as this polynomial. When are two polynomials the same? When they have the same coefficients. So the constant term of the left-hand side must be the same as the constant term of the right-hand side. That gives me A is equal to 3a minus 3b. That is by equating the two constant terms. Same thing for the linear terms. So b must be equal to 3b plus 2. I have the feeling that I'm... So what I get from this is I bring this to the other side, I find that minus 2b is 2, and therefore b is minus 1. That's great, right? I don't have to do really much. And now I can plug that in here. Then I get a is 3a minus minus plus 3. So if I bring the a to the other side, minus 2a is 3. So a is minus 3 halves. Okay, so I have b and a. So let's see what we have. Our particular solution is a, which is minus 3 halves, plus, so minus n. Okay. Step 3. And this is actually not hard anymore. The hardest part is this one here in the middle here, because we had to propose a solution and then find the coefficients. The new thing, let me put that. Now we put things together. We have to just be careful here. So don't forget that you have to add the homogeneous and the particular. Hold on. The particular. Now the homogeneous still has a constant in it because we have not yet used the initial conditions. That is at the end. So we have alpha to 3 to the n, that's the homogeneous one, plus, and what is the particular one? We have just written it down there, so it is minus 3 halves minus n. Okay, so that is 3.1. 3.2 is now use the initial condition. That was a1 equals, what was the initial condition? A1 was equal to 3. Okay, so that means what it means that if I plug in n equals 1 in here, I get 3 equals 3 alpha minus 3 halves minus 1. Okay, just plug in n equals 1. So if I solve for that, that is minus 5 halves, so that is 3 plus 5 halves is 3 alpha. That means 6 plus 5 halves is 3 alpha. That means 11 over 6. Alpha is 11 over 6. Okay, and so, conclusion, the solution was an is alpha 11 over 6, 3 to the power n, minus 3 halves minus n. You see, fractions are going to happen here because it's very hard to not get fractions. Okay, let's do another one. I want to do one here with the double roots here. Let me see here. Okay, let's do this one. It's going to be takes a little while, but I want you to see how it works here. So let's do the equation. An is 6an minus 1 minus 9 times an minus 2. I'm making it up a little bit, so I'm going to perhaps get wrong at the initial conditions, so apologize for that, but I'm going to take a0 is 3 and a1 is 9. It's going to give me fractions, I'm sure. Sorry, and I want, this is a homogeneous one, I want a non-homogeneous one, I want it to be 5 times 3 to the power n. Good. Step 1, the homogeneous. You can tell this is going to be, in a quiz problem, this is going to be a juicy one, right? There's a lot of work to do because we have to do the first homogeneous, that could take a little while. 6an minus 1 minus 9an minus 2, so the degree here is 2. Of course, the degree above is the same as the degree of the homogeneous, right? Yes, be careful. The degree, when we talk about the degree of a recurrence relation, is the degree of the homogeneous part. It has nothing to do with the degree of the inhomogeneous. It's nothing to do with the d that we talked about above. Okay, so degree 2 here. So what's the characteristic equation? Characteristic equation, so that's 1.1, right? Is r squared equals 6r minus 9. I hope everybody sees this. So this is r squared minus 6r plus 9, and that factors as r minus 3 times r minus 3. So that is actually r minus 3 squared. Okay, so 1.2, the homogeneous solution looks like what? Oh, this is 1.3 already. We solved 1.2. We were solving it. 1.3. The homogeneous solution, how does it look like? Remember what we have to do. We take any of the roots. There's only one, so that becomes the base of our exponential. And then we put here a polynomial of degree less than the multiplicity. So what's the multiplicity? Multiplicity of r is 3 is 2. So this will be a polynomial of degree 2 minus 1, 1. So alpha plus beta n. Okay, alpha and beta are unknowns. Remember, for the homogeneous I'm using Greek letters, and for the non-particular one I will use capital letters. That's it. Step 2. What is f of n? F of n is 5 times 3 to the power n. Okay, so let's analyze what is d. I'm not going to use colors anymore. Okay, what is s, what is d, and what is m here? So what was s? S was the base of the geometric. That was s is 3 here, right? So this is 3 to the power n. It's this one that I have to look at. Don't look at the homogeneous anymore. It's what we have here. So s is 3. Okay. What is d? That's the degree of the polynomial in front of that power, which in this case is just 0. It's a constant. Okay. What is m? What was m? That was the multiplicity of 3 in the characteristic equation. Oh, but wait, this is 2 now. So m is actually 2 in this case. So far we always had cases where we didn't have the s that we had was not a root of the characteristic equation, but this time it is. And it makes a difference because, remember, 2.1 says that the particular solution, I propose now, what do I have to put? Well, first of all, it is going to be 3 to the power n. Then I have to write down a general polynomial of degree 0. That means with these constants a, b, and c as coefficients, right? So degree 0 means just a constant, so there's just going to be an a here. And then comes here n to the power the multiplicity, right? So that's the factor that we have not seen yet, but I told you it's going to be there. It might be there, this guy. So this is n squared. N squared. Good. 2.2, what we do? Now, from now on, everything is the same. We plugged it into our original equation. So I write the equation again. an is 6an minus 1 minus 9 times an minus 2 plus 5 times 3 to the power n. Don't forget the inhomogeneous part, otherwise you're going to get in trouble. Okay, so plug this in. So I'm going to plug this quantity in here for n, then replace n by n as 1 and plug it in here, replace n by n minus 2 and plug it in here, and this is, I don't touch that one, that just is copied. Okay, so we get, I'm going to write my a first, a n squared 3 to the power n, then I get 6a, now instead of n I have n minus 1, and I have 3 to the n minus 1, minus 9, 6 n minus 2, there's now n minus 2, right, square, 3 to the power, well, n minus 2. And then this one, as I said, we just copied, 5 to the power 3n. So, this is now something, the first time that we see some more complicated thing like that. The next thing we do is divide out the highest power of 3, highest power of 3 possible. What is the best that I can factor out here, or divide out, is this power here, right? This is the lowest power, and I'm going to divide everything away. That means how many, there are going to be 2 powers left here, 1 power left here, no powers here, and 2 powers there. Okay, so let's do that. That's going to be a n squared. As I said, there were going to be 2 left here, so there will be a 9, 3 squared, right? Here we will have 1 left, so 3 times 6 is 18, a n minus 1 squared, minus 9, here we nothing left, so 9a n minus 2 squared, and then here we have what's left, 9, right? Because and 2 powers of 3 are still left, so 9, so it's 45. And you see, this is again an equation that involves this a, and hopefully we can figure out what a is from it. So we have to expand, and that's here where it gets a little bit writing down. We have to n squared minus 2n plus 1 minus the double product formula, right? And minus a, that's n squared minus 4n plus 4 plus 45. Okay, so what we don't remember what we did in this case when we were trying to solve this here. We were gathering terms of the same degrees, right? We would have the constant term, the degree n term, and so we're going to do exactly the same here. Let's find out what the constant term is, what the term of degree n1 is, and degree n squared is, okay? So let's first look for those that have no n in there, so the constants. That would be this guy times 18a, so 18a, this guy times minus 9a, that is minus 36a, and then 45 plus 45. Okay, and what is this? That's that guy, plus. What is the term with n? So let me put the n here. So we have one contribution from here, that is minus 36a. We have a contribution from here, that is 30 plus 36a, and nothing there. Okay, that's it. And then what is the contribution? What have we have with n squared? We have here one guy that is 18a, and we have here one guy that is minus 9a. Okay, so let's see, can we simplify things here a little bit? So 18 minus 36 is minus 18a plus 45. Great. Oh, look at that, minus 36 plus 36a is gone. And that is what needs to happen, because if that doesn't happen, I'm in problem. Okay, if this would be, for instance, say, a number that is not 0, then the problem is on the left hand side there is no linear term. And remember, the left hand side has to be equal to the right hand side. Okay, so it has to be 0 here. That's good news. If this is not 0, you made a mistake. Okay. Now what about the last one? You say, shouldn't that also not be 0? No, because we have something here. Yeah, but what about this one then? Hold on. Okay, so we have this. The term with n disappears, and then we have here minus 9 plus 9a n squared. This is exactly also another thing that I want. I want this and these two things are now gone. And so what I left with is, and you see here now, 0 is equal to minus 18a plus 45. So I can solve for a. 18a is equal to 45, so a is equal to 45 divided by 18, that is 5 halves. Yeah, as I said, it's almost impossible to not have fractions here. And we found out what 5 halves is, so we know that our particular solution, this means that this is a solution of the original equation. But it's not the one we want because it doesn't satisfy the initial condition. That's the problem, okay? So, did I give initial conditions? Yeah. Oh yeah, I gave the initial conditions. So, but let's write down first this one before, let's not run too fast. This is the guy, right? This here, so we have 5 over 2 n squared 3 to the power n. So, now step 3, we put them together. The solution that we're after consists of the general homogeneous solution plus this particular solution. The general homogeneous solution was this guy. Oh, there's still coefficients to be determined, right? So alpha plus beta n 3 to the power n plus 5 over 2 n squared 3 to the power n. But the next step, that's 3.1, is using the initial condition is really not such a big deal. Well, perhaps it is. Okay, so a0 was 3, I said, and where am I? A0 is 3 and a1 is 9. Okay, so a0 is 3, a1 is 9. Okay, so what we do is we put an n equals 0 in this equation. And then on the left hand side we get 3, on the right hand side we get alpha, 3 to the power, the beta goes away, this has gone away, oh, that's it, alpha is 3, great. And now we put in, so this was for n is 0, for n is 1, then we get 9 equals, then, okay, what we have, alpha plus beta times 3 plus, not forget, we also have this term, right, so 5 halves, 1 times 3. Okay, and we know that alpha was 3. So this is 3 times alpha, which is 9, plus 3 times beta, plus 15 halves. And then we can solve for beta, and we see that minus 15 halves is 3 beta, the 9's cancel, and therefore beta is minus 5 halves. So, conclusion, the solution of this recurrence relation with the initial conditions is alpha was 3, so it is 3 minus 5 halves n to the power 3n minus 5 half n square 3 to the power n. Not something you would have expected really that it comes out of that, but that's what it is. Okay, so I did a little bit of everything. I did examples where we have higher multiplicity, where this m is not 0. Okay, you see that certain cancellations have to happen. This is somehow the most special case that requires more work than the others. And I just want to do one more thing very quickly. We'll do a lot of homeworks and work it out, problems like that, but I just wanted to do one thing here. Suppose we have this same, let's look at the same the same recurrence relation. That was this one, right? Where was it here? Sorry, I'm just copying it. It's the same one as I used before, at least the homogeneous part. And so I'm just let's practice a little bit what are the, so I'm going to make a little table. If fn is this, given for certain fn's, what would be the corresponding particular solution be? But in order to do that, I need a little bit more space, of course. So given fn, I should calculate what the s is, what the d is, and what the m is. And once I know that, I can write down what the particular solution is. So let me show you what it will be. So what I did was, in the case that we worked, our starting point, ours was this one, right? 5 times 2 to the n. So let's say just 3 to the n. We saw that s is 3. That is always easy, right? That is just copying what it is. The d, that was degree 0 because there was nothing in front of it. And the m was 2 because 3 itself was a root of that characteristic equation with multiplicity 2. And therefore, we know that the general solution would be 3 to the power n times a polynomial, general polynomial degree 0, which is just a constant, times n to the power 2. Okay, so suppose my thing was 4 plus n squared 3 to the power n. What would then be the particular solution look like? Okay, and the other one, I'm going to write them up, let you think a little bit about it, and then I'll solve it. I mean, remember, you can always pause this video, try to solve it, and then, so the other one I want to do is 4n cubed 2 to the power n, and the other one is 5n plus 6n squared. Okay, let's see what they are. Okay, pause it, fill it out for yourself, and here I'm going on. S here is 3 again. What's the d here? Well, in front of it is a polynomial degree 2, so that is 2. And the multiplicity, of course, of 3, that's always stays the same, right? It's the same homogeneous equation, 2. So the general form is 3 to the power n. Then I have to write down a general polynomial of degree 2. That is a plus bn plus cn squared. And then in front of that has to come n to the power m, so this is n squared here. Okay? Of course, you can imagine this gets very ugly, right? If you start having to plug in, you see how high we have n to the 4th comes in there. Okay. In this case, what do we have here? Well, now s is 2, and therefore the multiplicity of that is 0 in the characteristic equation. And so that doesn't play. So what is d here? Well, this has degree 3. So how does this now look like? Well, 2 to the n. There is no n to the power. This part here is not there, so that's not going to be anything. So the only thing that I have to write is a general polynomial of degree 3. So a plus bn plus cn squared plus dn cubed. I hope you know your alphabet, right? You can go all the way up to degree 26. Okay. And then what is here? We're going on this one. Oh, what is s? Remember, if you don't see it, it means it's 1. What's the multiplicity? 0, because the only root of the classical equation is 3. So that's solves it right away. And what is degree? 2. So how does it look like? Well, 1 to the power n. That's the thing that we would have right here, but I'm not going to write that. That's silly. So the only thing I have to write down here is this guy, because this is also not contributing, right? It's n to the power 0. So the only thing is a general polynomial of degree 2. So this is a plus bn plus cn squared. Okay, I think you have now an idea how it works. There's several homework problems, but you see it gets long. And we will get a quiz on this. Yay!